Hello and welcome to Mutually Exclusive Events. Today we're going to look at probabilities of finding two things, probability of A or B. And there's two different ways that we can find this depending on the kinds of events that A and B are. Mutually exclusive events are ones that cannot both happen at the same time. Make sure you write this down. So their sets do not overlap at all. They are separate. The other word for it is disjoint. That means that there is nothing in common. They cannot both happen at the same time. For example, maybe event A is the event that a student is at Layton School. That's our elementary school. And event B is the event that he has his driver's license. Okay? So hopefully there is no overlap. Hopefully there are no students at Layton that are driving cars and have a driver's license. So those are mutually exclusive events. You can't have both. So if we wanted to then find the probability, if we reach into a student number bag and we try to pull somebody to see what's the probability that the person I select either is a student at Layton or has their driver's license, because they are mutually exclusive, all we would need to do to find this is add the probability of A to the probability of B. Done. Okay, because they're mutually exclusive, we can just add the two, and it's very simple. The probability of getting a Layton student plus the probability of getting a driver's license student gives us the probability of getting a Layton or driver's license student. But if two events are not mutually exclusive, there is an overlap, and that is the probability of A and B. That is this part right in here, the overlap. And so we need to subtract this in the formula. You can see the formula down here. Probability of A plus probability of B minus the overlap. Because if we take all of A, that's all of this, and we count all of that, and then we take all of B, and we count all of this, you can see there's a section here that has been double counted, this overlap. So we need to take A plus B minus the overlap if they are not mutually exclusive. Now actually this formula even works whenever they are mutually exclusive, except that if we subtract the overlap here, this part is just 0 because there is no overlap if they're mutually exclusive. So it's sort of like minus 0, which doesn't really change anything. We just don't really need to worry about it. But we do need to worry about it if they are not mutually exclusive. And so this is the formula that you absolutely need to get down that we're going to be working with. Okay, a couple examples. If we draw one card, what's the probability that it's an ace or a face card? So let's think about that first. Are those mutually exclusive? Could you be a card that is both an ace and a face card? Meaning a jack, queen, king. No, you're either an ace over here, and there are 4 of them, or you're a jack, queen, king face card, and there are 3 jack, king, queen times 4 suits, there are 12 of those. So the probability of being an ace or a face card, we can go up here to the first formula. Nothing that we need to subtract, there's no overlap. So we could just take probability of ace plus probability of face card. So that's going to be 4 out of the 52 cards, plus 12 out of the 52 cards. Add them together, 16 out of 52. I'm not going to worry about reducing right now. Okay, the second example says, what's the probability that it's a face card or a heart? So could you be both a face card and a heart? Well, yeah, you could be a jack of hearts, a queen of hearts, or a king of hearts. So we need to think about this one in that there's an overlap. We could have face cards here. There are 12 of those. There are hearts. There are 13 of those. But some of those there's an overlap. I just mentioned the jack, queen, king of hearts are both. So let's put those in the middle. And so out of the 12 face cards, that leaves 9 left. Out of the 13 hearts, that leaves 10 left. So now, because these are not mutually exclusive, the probability of a face card or a heart is going to be probability of a face card plus the probability of a heart minus the overlap, face card and a heart. So the probability of getting a face card altogether, there were 12 out of 52. The hearts, there are 13 out of 52, and there are 3 in the overlap. So that is 25 minus 3 is 22. And we won't worry about reducing right now, but 22, or I guess 11/26 would be the best answer. One more example here dealing with mutually exclusive. You may want to pause and write down this problem here. But then when I start it and explain, I'll talk through it a little bit. We have a business that pays overtime wages or, that's important, hired temp help for 9 months. So this is together. So let's get this information down. The probability of getting overtime wages or temp help is 9 months out of 12. So if we were selecting a month at random, the probability that we would get one of those months is 9 out of 12. Overtime wages were paid during 7 months, okay? So overtime wages would be 7 out of the 12 months. And temp help was during 4 months. What is the probability that an auditor will select a month in which the company was paid overtime and temp? So this is what we're trying to find. Let's go back to our formula. If you remember our formula here, whoop. We know this, we know this, we know this. We're trying to find this one. So, probability of of overtime or temp, that's here, that's 9/12, equals this one plus this one minus the overlap, the probability of overtime and temp help. So now I have an equation. I can add this to this side. And I'll subtract the 9/12 over to the other side. So I have this. And we're subtracting 9/12. So this gives me 11/12 minus 9/12 is 2/12. So the probability that we select a month at random, and it was a month that both had overtime help and temp help, was 2 months out of the 12. I hope this helps you to understand how we can use this formula to calculate mutually exclusive events. Have a great day.